All right, so here's where we're going. So I want to talk about Lab 4, which is posted. I want to do a rehash on Pt2. I want to talk about Printwriters, which will help you with writing your decision tree into a file. I don't think we did this. Did we go back and look at the short version of Pt2 using tree maps? Okay. So I want to go back and look at that because it's a useful example of using objects and building objects from objects. So I want to do some of that stuff. Then I want to talk about red-black trees, which is a different way to balance trees. And then we'll go back into some Java. I want to look at implementing trees in Java. Binary trees, decision trees, doesn't matter. Just kind of like look at some sample code and kick around some ideas about this if you haven't already gotten going on PA4. I want to talk about regular expressions as another example of using objects in an object kind of way. And I want to talk about Huffman coding, which is yet another type of tree. It's a binary tree, but it's not a binary search tree. It's not a decision tree. It's a tree that we build from a forest of trees by gathering trees together to make bigger trees, and the tree we end up with can be used to do compression of text. And it's a good algorithm to have seen and be familiar with. And I'm not going to give you an assignment on Huffman coding, but somebody else will at some point, I'm sure. So it'll be a good thing to see. So let's run through Lab 4 really quickly, and I think it's fairly self-explanatory. But just in case. Anybody looked at Lab 4 yet?
It wasn't up when we tried to look at it.
When did you try?
Thursday, I think.
Okay, because I posted it over the weekend. So Lab 4, playing with switches instead of LEDs. So the input side of things. So in your 223 lab kit, there should be a little switch. It's a tiny little thing with 4 legs and a black push button in the middle. Okay, that's the switch you're going to use. And your goal is to basically take this switch and hook it up to 2 ports on your Pi so that you can detect when the button has been pressed. So wiring is as simple as the LED. You're going to connect the switch between points 14 and 16 on the USB unit. Okay, so the same locations you used for the LED, but we're going to change those to be an input port instead of an output port. Okay, the switch will fit into the board, but sometimes you have to fiddle with it. Don't mash it and break its legs off or something, unless you have to. But it should fit in there, and it should stay in there. And your program's basically going to count how many times the button is pressed. And each time it sees the button's pressed, it's going to print out that number. Okay, so you're going to continually poll the port. Right, it's going to be a tight loop that just checks the port and sees if it's equal to the same value it was last time you checked. If it is, nothing has changed. If it's different, and if it was not pressed and now it is pressed, you've got a button pressed. So add 1 to your button press count, print it out. The next time that the value changes, you'll notice that it had been pressed and now it's not pressed. That's a release. You don't have to do anything for that, except note that now it's released. Okay, you did this in 270, but you did it in assembly language, and so it probably looked a lot more complex. So write your code, wire it up, and put in a flowchart or pseudocode describing what it does, and then get it signed off. And there's bonus opportunity here. So the bonus opportunity is that these push-button switches, like all switches, are noisy. They're mechanical in nature. You're pushing something down and a piece of metal is being made to make contact with another piece of metal. And when you release, that contact is broken. So there's some continuity between these two pieces of metal. But in reality, because there's springs and physics and things like that, when you press this down, it doesn't just go from no contact to contact, it bounces. And it'll make contact multiple times, even though you're just pressing it, right? It'll actually make and break multiple times. So when you run your code, it'll print out, a 0 saying there's no presses yet. You'll push the button, but it won't just print 1, it'll print like 1, 2, 3. And you release it, and it may print something on the release, because when you release, it doesn't just go from being in contact to being broken. It actually remakes contact a few times. So you may see some phantom counts when you release. And if you press it really fast and really hard, you might get it to count just 1, right? Or it might do worse. So your bonus is to debounce it in software. And how do you do that? Well, you take time into account. So there's a system.currentTime millis, which gives you the current time in milliseconds. And when you find that the switch was giving you a 0, it was open, and now it's closed, record what the current time is. And the next time that it changes state, that it opens again and closes, see what the current time is now and see how much time has passed since the last time you saw the button closed. And if it thinks that the button just closed again after 3 milliseconds, it's probably not a legitimate second button press. It's probably still the first button press bouncing. So you need to figure out what's a reasonable amount of time. How quickly could someone actually hit the button? So that if they can actually press it in 50 milliseconds, right, you want to count those as separate. But if you see another press and it's only been 3 or 4 milliseconds since the last one, that's a bounce. Don't count it. So that's your bonus target. So your demonstration, one experiment. The program should print at least one message each time the button is pressed. The count should increase, possibly by more than 1 following each button press. And the bonus is if it increments by exactly 1 after each button press. And the test is press it 10 times. It should go up by a total of 10. And you get to demonstrate that to the instructor within reason. Now, if you have to press and release and wait for 5 seconds and press and release, the instructor may say, let me try that. Okay? But if you get Mr. Super Fast Hands trying to test your circuit and they can break it, that's okay. Reasonable button pressing rate. Okay? So it's not an attempt to deny you your bonus points. But try to find a sweet spot between like having to wait too long and picking up phantom presses. Does that make sense? All right. And I gave you some possibly helpful code fragments. So the GPI controller line is still the same. That gets you an instance of the controller. But now GPIO pin digital input, GPIO.provision digital input pin, that lets us specify a pin as being an input source instead of an output. And in 250, 270, we always have these pull-up resistors, right? So our typical switch wiring looks like this. Here's our switch. This goes to the circuit. And we pull that side up to 5 volts through a 1K resistor. No, we don't. We pull this side up through a 1K resistor, and we ground out the other side of the switch. And now if the switch is open, we have a logic 1 going to our circuit, and if the switch is closed, we have a logic 0, right? Because our switches are either open or closed, so-called single pole, single throw. This lets us turn it so that it gives us either a nice 1 or a nice 0. But to do that, we need this resistor here. This is called a pull-up resistor. Well, Raspberry Pi, being a nice modern piece of equipment, we can say GPIO pull up down control, give it the pin number, and say PUD pull up down underscore up, and it will wire in this resistor for us. So we don't need resistors on switches anymore. We can just have a switch, and as long as we use this conditioning, internally there's a pull up resistor connected to it. So now all we have to do is ground out that input, and it'll see a logic 0. If we don't ground it out, it will see a logic 1. You can do that on the PIC processor too. They never tell you that. You don't need resistors there either. And then this is how we find out what the value of the pin is, pin.getState. And it'll return pin.state high or pin.state low. So if it's high, it's seeing a 1, which means the button's open. If it's low, it's seeing a 0, which probably means it's closed. So here's some code you can play around with. You can put this in and run it, and it'll just show you the state of that pin repeatedly, and you can experiment with it. Sound good? All right, that's due Friday. And once you do that, you got output, you got input, you got debouncing, you've got threads, you got everything you need. You can like take over the world with a Raspberry Pi Zero. All right, so that's lab 4. PA3, anything I want to say about PA3? So a lot of people were entirely successful on PA3. Okay, so I had lots of good tic-tac-toe games, some of which I could not defeat, but all of which I was able to delete in the end, so I guess I won. But there were a number of assignments where people were not able to get all of the mechanics working. So the first order of functionality was basically being able to click, draw a mark, right? Have the computer place a mark somewhere, click somewhere else, get a mark. A slightly less level of functionality, lower level of functionality, was when the user had to do all the clicking. There was no AI. So you click and there's an X, you click the next spot and there's an O, you click the next spot, there's an X, and so on. So it's like 2 people playing with the mouse instead of the computer taking an active role. And that's fairly easy to rectify. It's really, what do you do after the mouse click, after you update the board, after you call repaint? Instead of just exiting, you have to call something else that basically decides where the computer wants to move, and then does everything you just did again, but for the computer, right? Updates the board state, calls repaint, right? And then you go ahead and exit, and it's back to the user's move. There were some issues with sort of state mechanics where maybe it didn't notice when the game was over, which is really just kind of more things you have to do after you do the click and you update the board and you call repaint. You got to also do some checking for state changes. So are we out of squares? If we are, it's a draw. Is there a set of marks that are in a line? If so, then whoever just made that move is the winner, right? So you have to note those things, identify them, and then set some more variables, like game is over, so that the next time someone tries to click, instead of just going ahead and putting a mark in there, first you check to see if the game is over, and if it is, you say click reset to start again, or something like that. So there were various issues with those kinds of mechanics around state. And those are also fairly easy to rectify if you've got a clear idea how your system is playing out, kind of as a state machine. But you can make a state diagram for your game. It doesn't have to be a formal 250 state diagram. But basically, you know, you're in waiting for the game to start state, and you really stay there until the person says start playing, right? And that only works if you've already selected who's going first and what mark. And then you're in this playing the game state, and that really moves out of there when the user clicks, right? And you do these updates, and you either come back to that state if the game's not over, or you go to some concluding state if the game is ended. And you stay in that state until the person says, you know, play again, and then you come back to the original state. So all of these things, if you had issues, right, come by during office hours and let's go through your code. Okay, because this kind of state-based programming is something you'll encounter again and again, and it's worth investing more time to make sure that it's making sense for you. And most of the code I saw was probably a good 80% of the way there. Okay, so it's a good time while it's fresh in your heads to sort of nail down the last details and get it to click. Any other issues with that? Had a number of, well, not a number, but several games that I could not exit, and even when I like shut down the whole JVM, they were still hanging around, and I couldn't X them out, and I had to close Eclipse to get rid of them. So by the end, I just had like 6 or 7 different games going in the background that I just minimized. So that was interesting. I didn't take off for that. So any questions on PA3 in general, or in specific?
Would you have accepted colored squares as opposed to lines?
For a win line?
Yeah.
Well, it depends. So I said don't use buttons, and in general I took off if you use buttons, but I saw a few cases where people used buttons, but they actually did a lot more work than if they hadn't used buttons. And so I gave them a break, and in at least one case, all the buttons turned red wherever the win line was. And I went ahead and took that, because I thought it was a reasonable alternative. And apparently not everybody heard me say don't use buttons. If I do that again, I'll put it in the actual assignment. Don't use buttons. All right, so that's PA3. PA4. All right, what do you want to talk about with PA4? Besides everything. Anybody finished it? Yeah.
Can you explain, can I see the sample like output? Or
Have we run PA4 in here? I don't think we did. Let's go ahead and run it.
I think you said you were going to be working on that sample.
It turned out it worked fine. I had a corrupt database file. So again, you can assume that this file always exists, and it's not going to be empty to start. So I'm going to start with something like this. So a 3-node tree. Is it hard? If it is, you're thinking of a rock. If it's not, you're thinking of a pillow. So the file that corresponds to that tree would look like this. Okay, question, is it hard? Yes answer, rock, no answer, pillow. So let's play this. All right, so again, I want to string in your file named database in your main method that points to the name of the database file, so that I can change that one line to point to my own database file. So I'm just pointing to the file we just saw, which was 20q.txt. So let's run that. So it says, hello, shall we play a game? Think of an object, I'll try to guess what you're thinking of. You can wait until you ask the first question. You can say hit enter when you're thinking of an object. Okay, so somebody think of an object. Don't tell us what it is. Who's thinking of an object? All right, is it hard?
no.
No. Okay, you must have been thinking of a pillow.
No.
No. Okay. So we say no. And it says, you stumped me. What were you thinking of?
Applesauce.
Applesauce. Okay, so here's how this is phrased. Tell me a yes-no question for which yes means applesauce and no means a pillow.
Is it made out of fruit?
Okay, so, yeah.
Is it applesauce?
Is it applesauce? So, is it made of fruit? Thanks, I shall do better next time. Okay, so let's look at our 20Q file now, and it's changed. Okay, so the question is it hard? The yes answer is a rock. The no answer takes us to a new question. Is it made out of fruit? Yes says it's applesauce. No says it's a pillow. It's a strange world we live in. So this has been replaced with a question. Is it made of fruit? Yes, applesauce. No, pillow. All right, so somebody else think of an object.
I got one.
You got one, okay. Is it hard?
No.
No. Is it made out of fruit?
No.
Aha, so you must be thinking of a pillow.
No.
No. Dang it. All right, what were you thinking of?
Kirby.
Kirby?
Yes.
Awesome. We'll even use an uppercase. All right, can you tell me a yes-no question for which yes means a Kirby and no means a pillow?
Does it say Poyo?
Say what?
Does it say Poyo?
How do you spell that?
P-O-Y-O.
Okay. Does it say Poyo? Awesome. So now if we look at this, it's been updated. And now if it's not applesauce, instead of immediately saying it's a pillow, it'll ask us a new question. Okay? So this is growing and presumably getting better, although it's unlikely it's going to do really well against an arbitrary question. Unless we live in a universe with pillows, applesauces, Kirby's, and rocks. All right, so on the Linux server under /temp, there are some files. So there's a 20Q big and there's a 20Q big win. The win version has those control M's at the end that Windows likes. I don't know if you need that. Okay, my suggestion is if you're on a Windows machine, use 20Q big win. If you're on a Linux machine or a Mac, use 20Q big. So what does 20Q big look like? It's a big file of a decision tree. Okay, it's 40,000 lines, so it's about 20,000 nodes. With all kinds of good questions like, does it look weird to humans? And can it do everything?
Can we play around against it?
Absolutely. And it's got Papa Smurf with 2 spellings, and Craig Davis, and a shape-shifting alkalite, and all kinds of good things.
The question mark was something I was wondering about. So in your file, you're not putting question marks, but still adding them in the output?
Yeah, so we'll get double question marks on this one. That's okay. You can do whatever you like. I'm not going to grade punctuation. So if we want to run against this, it's very easy to change. I'll just have my database string point to that big file, which in this case is HomeNick files 20Q big. So I'll stop this one, and we'll go ahead and run this. All right, so who wants to think of a really, really interesting object now? Not that Kirby's not interesting, but one that we haven't already like loaded in deliberately. Don't be afraid. Your deepest, darkest secrets revealed. And recorded on the web. You got an object in mind? It can be. So I think this is for things.
Yeah.
Okay, like animals, I think.
Oh, for animals.
I think this is only animals,
Oh.
but I'm not positive. It's a crowdsourced database, so but it'll probably work best with an animal.
Okay.
Okay, you got one?
Yeah.
All right, can it fly? No? Is it a very small animal? Yes. Does it live in trees?
Yes.
These aren't always easy to answer as yes, no. Does it eat gum leaves?
No.
Okay. I don't even know what a gum leaf is. Is it an Australian animal?
They have them there, but
I'll
it's not exclusively no.
okay, we'll say no. Does it like to eat nuts?
No.
No. Does it have legs?
Yes.
Is it green?
Not exclusively no.
Okay. Does it have fur?
Sometimes.
Okay. Is it considered a lazy animal?
No.
That would be a sloth. Does it live in North America?
It does, yes.
Okay. Does it have stripes?
No.
Gum leaf eating zebra. Does it does it swing from trees?
Could.
Okay. Does it have a fuzzy head?
Sure.
Does it look like a bat?
The next question is it a bat? No.
No. Does it eat bananas?
No.
Is it a lemur?
No, it's a spider.
A spider? Whoa.
This is
In North America?
Okay, so what would be yes for a spider and no for a lemur?
Does it spin a web?
Okay. All right. Well, that's good. It's very rare this actually gets stumped. All right, want to try one more?
It very well could
Yes.
have been there, and I just answered something wrong.
You got one?
Do it, oh, yeah, I
Okay. Does it fly?
do. No.
Very small?
Yes.
Live in trees?
Nope.
Type of dog?
Nope.
Does it build dams?
Nope.
Does it have a long tail?
Not at all.
Not at all. Does it eat dirt?
Ooh. No.
Is it a native Australian animal?
Nope.
Does it live in a cold climate?
It lives in extreme climates, so yes.
Okay. Does it smell bad?
Oh, it's too small to smell. So no.
Well, it might smell bad to other ones. Does it have long ears?
Nope.
Is it used in experiments?
Oh God. It's studied but not used. No.
Are there at least 31 ways to cook it?
No.
I want to say yes just to see what it is.
Shrimp, probably.
Does it? Oh yeah. Does it live in Antarctica?
It does, and I think somebody already put this in there.
Does it participate in mass migration, often resulting in mass destruction?
Oh God, no.
Is it microscopic?
Yes.
Can it live in hot and cold places below zero and loses 90% of its water to stay alive?
Yeah, somebody already picked that.
Is it a water bear?
It's a tardigrade.
That's a
It's a
yes.
water bear.
Is
Yeah.
that the same thing? Okay, yes. Cool.
Right.
All right. So this was crowdsourced, right? And it in some sense gets better the more you play it, as long as your answers are honest. The more times you play it, and it gets your answer wrong, the better it's going to do in the future. So some would call this AI, or at least some sort of learning system. A decision tree is a really basic type of way to code information, to code knowledge, right? So there's things like expert systems, which was the big push for AI back in the 90s. Everything was going to be an expert system, and it was going to change the world, right? Today it's deep learning. So decision trees are interesting. You can do lots of interesting looking things with them. So PA4 is a chance to play with that. And looking at this file, right, it's pretty hard to know immediately like how it's going to play out by doing yes, no kinds of things. So what was the thing we just put in? Spider.
November spider, jumping spider.
So there's lots of different ways to get to a spider.
Right.
Does wear a pale face, have spider-like fingers, and spend most of the day plotting new ways to destroy Harry Potter. Nice.
Is that an arachnophobia reference?
Maybe. Okay, so that was the one we just put in, right? And it came right before lemur. But it's pretty hard to know that would have been the right place to add that question and answer, just by looking at the file itself, right? So again, we don't really monkey with the file directly. We do the following. We read the file and use it to build a tree, and then we play game. If we make our final guess, which is wrong, adjust the tree, and then write the tree into the file. And then go back up here. That's your whole PA4 in a nutshell. Okay, one time in the very beginning, read the file, use it to build your initial tree. And then just go through a loop where you play the game. If your answer is correct, nothing to do, go back, play the game again. If your answer was wrong, make that adjustment to the tree, and then write the tree out to the file, the same file that you started with. Okay, and every time that you play the game and you get the answer wrong, make an adjustment to your decision tree, write the tree back out to the file. So once you're done and you exit, right, the next time you play, the file that you read is going to be the final augmented tree that you were working with last time you played. So it retains that knowledge. So writing the tree to the file, that's just doing this pre-order traversal. Right, pre-order traverse and write out each node as a 2-line entry in the file, either question colon or answer colon, followed by the data. Reading the file is that recursive algorithm we looked at. Right, read the first 2 lines. If it's an answer, just make a single node and return it. If it's a question, call the ingest routine recursively twice. Set the left node equal to the first return, right node to the second return, and then return that tree. And then playing the game is start at the root. If it's a question, print the question, wait for an answer, go down to the left or right subtree. Do that until the root's no longer a question but an answer. At that point, print out the answer, see if it's right or not. If it's not right, then you need to get a new question, right? Get what the correct answer was, get the question that tells you whether it's yes or no, and then whichever node was your previous question, your previous answer, right? Replace that with a new question and the 2 new nodes. When you define your tree, instead of defining a dot left and a dot right, you might want to define like a dot yes and a dot no. So you don't have to keep track of which one's left or right. That's legal. So to get started, if you haven't started, right? Define a tree node. Define a tree. I would say put together a tree by hand. Just write some Java code that builds something like, you know, this decision tree. So make a node, set this to is it hard, make a node, set it to rock, this thing, and put them all together just manually inside your Java code in your main program. And then see if you can play the game, right? Make a method that you pass it a tree, and it does this business of here's a question, let's ask it, let's go down to the left or the right and keep going till you get to a leaf node and then print out the answer. Don't worry about augmenting the tree, don't worry about file I/O, just worry about the mechanics of starting with the root and going through and playing the game. And once you've got that working, you've got a really good framework to build on. Okay, now you have to deal with adjusting the tree if the answer is wrong. That's probably the most subtle part of the whole thing. And then you need to be able to ingest the tree once in the very beginning, and you need to be able to write the tree each time you adjust it, which is probably the simplest part because it's just a traverse and write.
Say we get it working, but we want to make a GUI afterward.
Mm-hmm.
Is it pretty easy to put that in after?
As long as you're modularizing, right? So I might do something like this. So right, I'll make a read file method that I give it a string containing the name of the file. That's your database string. And it ingests the file, builds a tree, and then returns the root of that tree. Okay, so that's my initialization. While something, I don't know what, while forever maybe. You make a method called play game. You pass it the root of the tree, it goes through, plays the game, figures out if you got it right or wrong, and so on and so forth. And in the end, it returns the root of the tree, possibly which has been augmented by having gotten the answer wrong, right? call a write tree method, give it the name of the file, and give it the root of the tree. So that's your main loop. So inside here, you're going to have something that says, you know, take the node pointed to by the root, print out the data, wait for the next line from standard in, and if it starts with a Y, then do this thing. If it starts with an N, do this other thing. Otherwise, yell at them and go back and get another line, right? So you want to replace that with a GUI, right? So you have a text field maybe, and instead of saying print line, you know, whatever the question is, node.data, and you'd say text field dot set string parentheses node.data, or whatever the method is that you want to use. And then instead of having a while loop where you're marching down the tree, right, you could have a variable that's your current pointer, your current location in the tree. And after you've printed out the question, you just exit. And you have a button handler for the yes button and the no button. And the yes button says, go down to the left branch of whatever our temp pointer is, right? Set temp equal to that, print out the question, exit. No button, go down to no branch, right? And then in there, if you get to a node and it's actually an answer, then you go ahead and you print out the answer and do whatever. But it's pretty easy to pull it apart into event-driven. All right, let me touch on Printwriters, because this will make your life easier. So Printwriter is probably your easiest way to send output to a file. Okay, Scanner is an easy way to ingest. So when you want to read from a file, you can say something like Scanner. Right, so create a new file object with the path to the file you want to read. Use that as the constructor for a new scanner. And the object it returns, if you say file in dot has next line dot next line, it'll read from the file instead of standard in. Okay, and this has to go in a try catch block, because if the file doesn't exist, it'll construct the file object fine, but when you pass it to scanner, it'll throw an exception. So Eclipse will warn you about that. That's what's going on. All right, so Printwriters let you go the other direction. They let you write to a file instead of writing to standard out. And you can construct the same way, Printwriter, and you can give it a file object. So we could do something like this. And that'll construct a Printwriter object PW that lets us write into this file called haha. So let's just do that. So this will be called Printwriter. We'll make a class. Give ourselves a public static void main. So I don't have a ha-ha in here. I have a ha. Let's get rid of ha. All right, so import these things. And import file. And put around your try-catch block. It does it all for you. There's an option for completing CSE 223, but we disabled that.
And Control Shift / puts it in a comment block, and / takes the comment block away.
Okay, cool. So be aware if I try to use PW here, it's going to complain that it doesn't know what PW is because I declared it inside a try-catch block. Okay. Now I could put all of my code right here inside my try-catch block, but I don't want to go crazy with that. I don't like being nested any deeper than I have to. It confuses my brain. So the better solution is to declare my Printwriter outside of the try-catch. That was freaky, man. Okay, so I'll declare my PW variable outside, and then it's going to complain that it may not have been initialized. So just to make it happy, I'll give it an initial value. And who knows what it's complaining about now. Oh, I just need more stuff. So what can you do with a Printwriter? Well, we can say pw.println, and it will look like system.out.println. And then close your file with pw.close at the end. So, Printwriter object, open it up with a new file that's constructed with the path name of the file you want to create, and then just pw.println instead of system.out.println. So, no ha-ha here. Go ahead and run your code. And now there's a ha-ha, and it's got our text in it. Okay, it's that simple. So I'll slam this code up on the server under the code samples area you can get to. All right, so that's all you need to do outputs. All right, so Wednesday, let's look at a better version of Pt2, okay, using tree maps. We'll finish balanced trees, looking at red-black trees. We'll code up some trees, and we'll go on from there. Sound good? All right, I will see you next time then.